Welcome to Pi Excellence Tutorials. If you happen to be looking for a private tutor or someone to help you in your assignments, you can get in touch with me on using the details that I've dropped in the description box. Yes, and if you have not yet subscribed to the YouTube channel, you can kindly subscribe, and don't forget to hit the notification bell so that you get notified each time I upload a new video. So in this video, we are going to derive the equation of energy stored in the spring. Okay, so a spring that obeys Hooke's law has a spring constant K. Show that the energy stored show that the energy stored in the spring when it has been extended elastically by an amount X is given by W being equal to half kx squared. Okay, so I'm going to take you back to see where the derivation is coming from, where everything is coming from. Okay, so it's going to be a bit long, but I want you to, because I'm going to do step by step. So I want you to follow me very closely. Okay, so we are going to start from linear harmonic oscillator equation. Okay, so that is the equation. So now, when you see the double dots like that, it means that y has been differentiated twice. So we're going to reverse this. Okay, we're going to reverse this. I don't know if I'm doing it in a hard way, but okay, so we're going to reverse this. And then I want you also to remember that this is the angular speed. And we know that angular speed is given by that. So angular speed squared is actually k over m. Okay, so I've said this means y has been differentiated twice with respect to time. So we have plus equal to 0. Okay, so now this one we can write it also in terms of velocity. So it's going to be, okay, before we write it in terms of velocity, let's replace the omega there. So we have plus k y being equal to 0, like that. Okay, so it's the same. So we can write this in terms of velocity, where we have dv dt plus k over m y equal to 0. Okay, so we can multiply this equation by m, of which we're going to have m dv with respect to time equal to ky equal to 0, like that. Okay, so now we can multiply change in velocity with respect to time by 1, and this one is going to be change in y with respect to y. So this is the same as 1. Okay, we haven't changed anything. We're just playing with this equation here. So we're going to have m dv dt multiplying by dy plus ky equal to 0. Okay, so now we can swap the denominators here. This is multiplication here. So we're going to have m change v with respect to y, change in y with respect to t. Okay, and we're going to subtract both sides by ky. So we're going to have negative ky this side. So when you look at this, what comes into your mind? This is actually velocity. So this equation is going to look like v, that is for this in, is it purple? Is it, I'm not good with colors. Okay, dv dy being equal to negative ky. Okay, so we multiply by change in y to this equation, and then we're going to have m dv being equal to negative ky dy. So this, which you have seen here, is actually a differential equation. So we integrate this equation. So I may say we integrate from 0 to v, 0 to y. Okay, so when we integrate this, we're going to see that v is going to be integrated and m is constant. So we're going to have half m v squared plus c1, that's a constant after integrating. And here we're going to have negative k outside, it's a constant. And then when we integrate y, we're going to have half as well, okay, y squared plus c2, a constant as well. Okay, so we can have mv squared and add half ky squared both sides, when we're going to have plus ky squared this side, c2 minus c1. And remember, these are constants which just equal to c, and this c is going to be equal to the total energy stored. Okay, so total energy stored is going to be half mv squared plus half ky squared. Now, when you look at this equation here, it's getting interesting. When you look at this equation, when you look at this part and this part, this is actually kinetic energy, and this is potential energy as well. Okay, so we look at, we got to the equation of displacement. Okay, now we know that when a particle displaces, we have a cos theta minus I, and that is the phase angle. If we happen to have the phase angle, that would be the phase angle. So we have that. So now, okay, so I'm going to use, okay, so here I've used y. Okay, in this case I've used y, so I'll put y here, but you can use x, you can use y. So me, I took it in the vertical, that I'm using y in the vertical. So you can even use x, there's no problem. You are still going to do the same thing and get the same answer, only that the only difference is going to be the y and the x. So you're going to see at the end, we're going to have ky squared instead of x squared. Okay, so now that is why now we need to find the velocity that we put there. So for us to get the velocity, we have to differentiate displacement with respect to time, of which it's going to give us negative that sine k that. So we have these values, we can place in this equation. So we're going to have half m, and then v squared, we're going to have negative okay, so let me use that. So this is squared, and then we have plus half k, and y is cos y also is squared, like that. Okay, so multiply, so we're going to have half m, and when we multiply this, it's going to give us a squared omega squared sine squared that, and then we're going to have plus half k a squared cos that. Okay, so now remember what we wrote at first. Okay, what did we write? This k, we wrote that we know that angular because is given by that, so we have, we have we have k, and that from that relation being equal to m omega squared. Okay, so now we replace this part into k there, where there is k there. So we have half m squared plus half, where there is k, we have that placed cos squared. Okay, so now we can factor out what is common here. Okay, you can factor out what is common, and what is common is half m a squared, okay, omega squared, and then we have sine squared plus cos squared. Okay, so when you look at this one, this is actually, when you look at this, this is actually a trigonometric identity. It's an identity, this one, and which is equal to 1. This one is equal to 1. Sine squared, sine theta squared plus cos theta squared is equal to 1. So the energy stored is half m a squared, like that. Okay. Okay, so omega, we know that omega here is omega squared is k over m, so we have half m a k over m. So m and m goes, and then we have half k squared. So now we've been taught to say this part, is this the particle? Let's check. Let's check out the statement. Okay, so now let's look at this. So we've been taught that The spring has been extended elastically by an amount of X. So this is an amplitude is actually the maximum displacement. So it has been extended to that, having that amplitude being equal to X. So half K X squared. It's shown. So this is how we get to derive that one. It's not difficult. It's just easy. You just follow steps. Okay. Thank you so much for watching. Look out for the next new video. Make sure you comment, give me feedback so that I know where we need to improve. Thank you so much for your time.